So some examples and problems using the idea of the second derivative. So if we got to look for the values of x for which this curve is concave down. So if it's concave down, we know the second derivative then would be less than 0. So that's what we need to find. We need to find that second derivative to talk about concavity. So we get our first derivative, so we derive that function. And then we drive it again, so derive 3x squared minus 6x, that gives us 6x minus 6. So it's concave down when the second derivative is less than 0. So if I put the second derivative, set it less than 0, solve that inequality, we get x less than 1. So it just comes down to getting ourselves a linear inequality and solving it. Find the stationary point on x cubed and show it's a point of inflection. So we get 3x squared equal to 0, so that's the first derivative. We set that equal to 0 because if it's going to be a stationary point, our first derivative is equal to 0. So we must get x being equal to 0, so if x is equal to 0, we sub it in to get y is equal to 0. And then if we get our second derivative equal to 6x, and we test that x is equal to 0, when x is equal to 0, we get the second derivative equal to 0. So it's actually what we call a horizontal point of inflection. So that's when we have a stationary point and it's also a point of inflection. So a gradient stays the same on both sides. So it's rising, 0, rising again, but it also changes concavity as well. So this time, point of inflection on the curve here. So we get our second derivative. So derive the function, derive it again. So we're going to get x is equal to 2. So the y value would be minus 27. Now, as we said before, we need to be able to test for a point of inflection. So if we need to get our value of 2, test either side of it. So we put 1 in, and if we put 1 into the second derivative, we get a negative value. So 12 times 1 minus 24 gives us minus 12. And we put 3 in, we get positive 12. So see that there's a change in sign. It goes from negative to a positive. So it goes from concave down to concave up, and at 2 there was no concavity. So it changes concavity. So we can say that because there's a change in sign, there's a change in concavity, and thus there must be a point of inflection. That's what we need to do to prove that. We need to be able to show that there is a change in concavity there. So there must be a point of inflection. So that's an important point to do, because we just can't say, well, it's equal to the second derivative is equal to 0, so it must be a point of inflection. Not always. As we said in the last video, sometimes that doesn't occur. So you've got to be wary of that. So that's why we just do a quick test, put it in the table, test that it works, and if there's a change in sign, then there must be a change in concavity. So that's when we get a point of inflection.